Yeah.
Hi guys, welcome to the 9th week of Wiz Mumbai webinar series. I'm Aksa and I will be your host for today's episode. So, the Women in Data Science Initiative, abbreviated as WIDS, aims to inspire and educate data scientists worldwide, regardless of gender, and to support women in the field of technology. WIDS Mumbai started off in 2018, where we hold independent events in the month of March. It is an independent event organized by WIDS ambassadors to coincide with the annual Global Women in Data Science conference held at Stanford University. You can find more information about WIDS Mumbai on our website. Our WIDS Mumbai webinar series has been going on for 9 weeks, and this is the 10th week of our webinar series. We took a poll, and you guys decided that you would like to have a code along workshop. So here we are. This is a second code along workshop, and today with us we have Kirti Khade. Kirti Khade is currently completing her education at a University of Queensland. She's doing her master's. She's a data science enthusiast, and she likes to play around with machine learning, applied statistics, data analytics, and data science. She has cross-functional experience encompassing sales and marketing analytics, supply chain analytics, and content analytics across sectors. She's well acquainted with data analytics tools and languages such as Excel, Python. She's constantly striving to upskill herself with latest technologies and techniques in machine learning, statistics, programs, artificial intelligence. So we're very excited to have you along and learn about neural networks today.
I'm excited as well.
So over to you, Kirti Khare.
Okay. Uh, so you can see my screen, right?
Yes.
Okay. Uh, so can we get started?
Yes.
Okay. Uh, Okay, so this workshop is essentially introduction to workshop, and like Aska said, this would be a code along workshop. But before coding, I would just like to give a quick introduction of what neural network is and from where it began, and some basic aspect of it, so that it's easier to code. Okay, so we'll start with the perceptron, which came into play in 1960. Okay, and the way it works is that it takes several binary inputs and it produces a binary output. Okay, so for example, it helps making human decisions like, will you attend this session? So what are the factors which will decide that you will attend the session or not? So the first would be, are you interested in this topic? Do you want to learn about this topic? Do you think the timing match, and so on and so forth, right? So that's your x1, x2, and x3. Like, does the timings match? Do you are you interested in the topic? Do you want to learn about this topic, and so on and so forth, right? So once you have those decisions, you map this decision and get the output. The output is essentially, will you attend the session or not? And now each input has a weightage, right? The first input. So for example, are you interested in the topic? Maybe that has more weightage than do you have time for it, right? So each input that we have has a weightage, and it also there's also an inherent bias, right? So maybe you're not free in the evenings, maybe you don't like the live sessions. So that kind of bias, which is also known as B, we have that. So we have a weight for every decision and we have a bias for every decision. Once we know all the points that help us to make the decision, and we know the weights for every point, and we know our bias, we can finally have the output, which is, will you attend the session or not, right? So this was the perceptron that was made in 1960. Now, the modern day neural network is just the complex perceptron. Okay, so we have an input layer and we have an output layer, and in between those input and output layer, there are millions and billions of hidden layers. Okay, So essentially, you decide how many hidden layers you want. You decide what is the input that you give, and you decide what the output you need, right? So that's your neural network. One important thing to note here is that any change that you make in any layer gets reciprocated to your output, right? So you need to make sure that whatever changes you're making, whatever weights you're deciding, and whatever function that you're deciding here is in the form that it gives you the target output that you need, right? So these function here are also known as activation function. Ashka, please stop me if I'm going too fast or if something is not understandable. Okay. Okay. So yeah.
Sure.
So now, yeah. Okay. So we have this activation function, and these activation function are like you give an input. There's an activation function. The activation function takes that input, gives out an output. Okay, so that's the function of an activation function, which is located into this circle, as we can represent it. These activation function can be of many types. So the most common ones are sigmoid function, which is ex divided by ex plus one. The one of the most essential characteristic that this activation function needs to have is it should be differentiable, right? Why? It's because neural network needs to have backpropagation. And what's that? I'll come back to that point below. Okay. So you have your sigmoid activation function, you have your step function. So we have 0 and 1, that's your step function. Then there's something which is very famous these days, which is called as Relu, okay, which is rectified linear activation function. And it's essentially 0 for anything which is less than 0, and then for the others it is linear. This function is very good when it comes to the vanishing gradient problem that neural network has. Okay, what's that? I'll come back to that later as well. Uh, okay, so that's your activation function. Now coming to the backpropagation, what happens is, let's say this is your neural network. This is your input, and once you have those inputs, you have your functions, you have initialized some weights, you get your output. But that output is not say does not match your target, right? And there is an error between both of them. Okay, so what happens is once you know what the error is, this error gets propagated to every layer, and it tells every layer that okay, you need to improve this much in order to get a better output, right? And then each and every layer that you have, you'll have to tell that. So that means that it's going to be a very long process if we have thousands and 10,000s or millions of hidden layer here, right? So because of which the neural networks are hard to train, okay, and that's why they take a lot of time, because once you know that there's an error, you have to propagate it to a very large number of inputs, right? Um, so that's your backpropagation algorithm. How do they do it? Is essentially by an algorithm called gradient descent. I don't want to get a lot into it, but just to give you a brief about it, what gradient descent does is, let's say this is a cliff, okay, and this is a ball that wants to get to the minima, right? Because every object wants to go to the minima of their state. So what happens is it goes here, and then like the ball will go here, and then it'll since it has a momentum and it has some velocity, it'll keep on shuffling, right? And ultimately before settling down, it'll go through a few local minimas, but what it wants is a global cost minima. So during the training process, every point have to find out what their global cost minimum is and settle down to that point in order to get the required target, right? So obviously a very difficult process, and one of the main reasons why neural networks take so much time. I hope that's clear.
Yes.
Okay.
You can continue.
Yeah. Okay. Okay, so again, to define this, there is a loss function and optimizer. The loss function tells you how do you measure the error between the output and the and the input. Okay, so depending on what kind of output and the target you have various kind of loss function. So for example, if you have a regression analysis, you'll the loss function that you'll use is a mean squared error. Okay, and what that means is that for every point that you have predicted, you will understand what the difference between the prediction and the target is, and you'll mean square and then you'll take the squared of the mean sorry mean of the squared, right? So that's for your regression. For so we'll today we'll be dealing with probabilistic loss, which will be the which essentially what happens is when you have different classes, you want to predict which class should a particular instance belong in. Okay, and which means that for every class I'll tell you what is the probability of being in that class, and then what we'll say is that we'll choose the prediction which will have the maximum probability, right? If the point has maximum probability of being in one class, we'll choose that prediction. Okay, so the cross entropy essentially tries to reduce the randomness in a system and the noise in a system, and it produces a categorical classes which will help us to find out which instance should a data belong in. Okay, so now um, this might be confusing right now, but as soon as we start coding, I think it'll be fine. Again, for the kind of optimizer that we need here, it would be the stochastic gradient and the Adam optimizer. These two are very widely used in the industry. There are a few others which you can just easily Google optimizers in neural network, and you can learn about them. When do they work? When do they don't work? Again, that's something which comes with experiment. So you experiment and understanding the kind of data that you have. Okay, for this session, we'll be using Adam. But yeah, we can as well use stochastic gradient as well. Okay. Okay. So now we'll start the main part of the session, which is coding. Uh, okay. So to do this, the functions that I'll be needing is the TensorFlow, the cares, TensorFlow cares, and matplotlib to plot. Okay, and then NumPy. And if there's any warning message, I just don't want to see them because they hide the output, and that goes below, way below. So I don't want to do that. Okay, so I'll start with loading the data. I'll be using something called an MNIST data, which I'll just show you right now what it looks like. So I need keras datasets.mnist, and then I need X train and Y train. So if you guys are coding along with me, um, is that the case, or will you be coding later, Aska?
So it actually depends individually, like what they prefer.
Okay.
Is there some recommendation you have for people who are coding along?
So if you are coding along, uh, um, should I send this to Google Colab so that everyone can see what the code is,
So,
or
so we will link the collab link down below in the video. So
okay,
now
that
you can
makes sense.
continue with the screen that you're sharing. Yes.
Okay, okay. So this is fine, right? I'll just
Yes.
code and I'll just commentary on what I'm coding about.
Right.
Okay.
Yes. Absolutely.
Cool. So I think Julian had a question. Which have you used any other activation function other than Relu in real world application? So there's one activation function which is Leaky Relu. It's basically so what happens. So the problem with Relu is that anything which is less than zero is essentially zero, right? So I mean we lose all the data which is less than zero, and there are many times when we don't want that, so which is why we use something called as leaky relu. What it does, it has some leaky data. I mean there's some data It's not as good as the one which is above 0, but there is some data below 0. Okay, and it also has where it also helps to improve the gradient vanishing gradient problem that neural network faces. So that is a very good activation function as well. Okay, moving on. So what I've done here is I've loaded a data called MNIST. This is like the okay. So this is like the data set which I think everyone that I know have started with this data set. So it's like really basic, and since it's already available in a package in Python, you don't have to really code for it. So that's something which is good here. Okay, and for again in Keras, there are a lot of data sets which are there. You might want to explore those. Okay, so right now what I'm using is MNSIT. You could also use Boston Housing Fashion. MNIST is like MNIST but for fashion. IMDb is for a movie recommendation, and CIFAR is for image data. Okay, so these are like really nice data sets because you don't have to process a lot. It's readily available, and which helps a lot in the beginning, at least like when you're starting out. Okay, so I've loaded the data. So I just want to quickly show you how it looks like so that you get a feel of it. So let's just have like the first uh, element of the trained data, and I'm going to just want it to be a little bit pretty as well. Uh, okay. Okay, so as you can see here, MNISC is essentially a handwritten data set of digits. Okay, so this digit is essentially 5, and if you will see the label for this data, so LBY train 0. Okay, so this is essentially 5. So in X train, we have the training data, which looks like the random images of digits written by hands, and the labels are essentially the labels that we want. Okay, so yeah, like every other data set, data science process, we have train data, a test data. This is a supervised learning, so we have Y train as labels and X test as the label as well. And the test data is not seen by our model; we just see the train data. Okay. So if you'll remember, every machine learning process has like input and then the output. Okay, so okay, so I'm just also going to print what is the shape of our training test data, and the labels as well. Uh, so it's going to be, yeah. So we have about 60,000 data points. Each have a shape of 28 into 28. Similarly, for tests, we have 10,000 data points. Each have a shape of 28 into 28. And for train, we just have like one digit. Like so for by train, we just had 5. So 60,000 times we have just one digits, and by test has 10,000 times just one digit. Okay. So I hope you understood what the data looks like. Let's try to model it. We have 28 into 28. The data is like 28 into 28, but you can't use that, right? You need to somehow make this into an input layer so that you can send it to your hidden and the output layers. So what you do is you take each and every pixel, and once you multiply 28 into 28, it comes out to be 784 neurons. Okay, and you take those hidden layer, take those input layer, send to the hidden layer, have some maybe some weight activation, and if you don't want, you don't have it, and then the output. So the output, as I told you before, will have probability for each of them, and we're going to see which one has the highest probability, and we're going to choose that particular class. Okay, so let's try to model it. And but before that, what we have to do is uh, we have to normalize the data. What does that means is that if there's any random points between the data which won't which will hinder the process later, we want to remove them. Then we want to normalize them. Okay, so we want to change the value of all the columns into a common scale. So I'm just going to do that. So there's a function called categorize.utils.normalization. Okay, and uh, and then in that function, I have to give the input as the train. The other input that it needs is the axis. Okay, so the axis could be 0 or it could be 1. 0 is essentially the row wise. However, we generally do it column wise. I didn't quite find anything which tells why that's important in an image. If we have a normal data, for example, if we have a data of sales, we have to do it row wise, because every row will sorry, we have to do it column wise because every column will represent a field. However, in image data, I don't think that that's the rule. I think we just do it because we always do it that way, and it doesn't matter. So I'm going to do the same thing for test as well, because why leave that? Uh, okay. And then once I do that, I'm going to, we should see this data as well, right? Like we saw it before, we should see this data as well. So we're just gonna see the data, and some spelling mistake. This one. Okay, I did some spelling mistake which I don't know about, so I'm just going to Google this. Okay, it is normalize. Okay, so Google, like I just want to minimize my Google count, so I'm just keeping a track of my Google count. So it's 1. Okay, so this is how my normalized data looks like, while this is how my non-normalized data looks like. But normalization is one of the most important step which you should do before using your data. Okay. Now the other step that we need is we need to convert the data to categorical, the labels to categorical. What that means is that we're gonna say we're gonna put a one hot encode on a y label. What that means is my y train, I want it to be curious dot utils dot to categorical. Okay, and then y train. So how does that looks like? Okay, so initially it was 5. Now it's converted into 0, 1, and it will be the 1 will be on the 5th element, right? So 0, 1, 2, 3, 4, 5. Okay, and the same thing I'm just going to do it with my test data as well. Okay, because you want the train and the test to have similar kind of processing, that whatever you do in train, you should be doing it on test as well. Not every kind of processing, you should not do every kind of processing, but at least the normalization you can do. Okay. So finally, we're going to model it. This model is going to be extremely simple. Model will be equal to sequential. Why sequential? It's basically sequential because it groups a linear stack of the layers into your model. Okay, because what you want to do is you have an input layer, you want a few hidden layers, and the final output layer. So for now, for the first one, we're just going to do one hidden layer. But what you want to do is you're going to stack each layer on top of each other. So you have to use sequential. Once you have that, you're going to add layers to it. So I'm going to add. So the first thing that I need to do is flatten. Okay. Why do I need to do that? Is essentially because uh, I had 28 into 28 pixels, but I want everything to go uh, one after the other, like one input, right? So 28 into 28, which is 784. So to do that, I have to flatten everything and and put it together. The other layer that I'm gonna add would be dense. Okay. Uh, for dense layer, so every other layer after this flattened layer is essentially a dense layer. Okay, so dense layer means that everyone is connected to each other and they give a dense view, right? So this looks like something dense. I think that's why they named it dense. Yeah, so that's your dense. And let's say I want to do 128 uh, dense layers, and the activation I need to be uh, I I really like Relu, so I'm just going to do that, and that's all. Okay, and the model dot add. Okay, so this is how I treat my input layer, so that it becomes flat. This is my hidden layer, uh, and then I just want the final output. Okay, so for that, I am going to have 10. Why would I have 10? And what activation could I have? Any thought, Ashka? Or any other in the live chat?
It is AXA actually.
What?
AXA. It's AXA. AQSA. AXA.
Oh, okay. Ah, okay, sorry.
So, that's what I'm not sure. So the activation spelling, there's a typo.
Yeah. Okay, so how do we decide? So the output that we need is essentially 10, right? Because that's the number of digits that we have. Uh, and if you'll see in our one hot code of the Y train as well, there'll be okay, there'll be 10 points. This is because we have 10 labels. Okay, so that, and the activation that we'll have is sigmoid. That is because it will give you the probability of this point being in all the classes. Okay, and then we're gonna, so when we finally predict, we are just gonna take the maximum output of it, a maximum, the one with the maximum probability. Okay. uh, okay, activation.
And for the hidden layers, like we put 128 layers. So how do we decide, like for different types of data? How do we decide?
128, yeah, okay, I'll come to that. So that's something called hyperparameter training. Very good question. Yeah. Okay, so once we have that, we are going to compile the model. Uh, which means that once I've defined my model, need to define my what's my optimizer is going to be. Okay, and then I'm going to define what my loss is going to be, and then I'm going to define what my matrix is going to be. Okay, I think like somewhere above here, I talked about what kind of loss function and optimizer we have. So I'm just going to use that detail. So optimizer Adam. Okay. Loss function, what I want is categorical, right? Categorical cross entropy. And the matrix that I'm looking at is essentially accuracy. So you could look at into many matrix. You can possibly look into just one of them. So that's what I am doing right now. Uh, okay. And then once I have that, I'm going to fit my model. What does that mean is now my model is ready, my inputs is ready. I'm going to fit my model, and the number of inputs that I have have is it's like I'm just putting approaches as 3. What approaches does it takes the data and it runs it multiple times so that we get a better accuracy while we are on our last approach. Now, the number of approaches that we generally set in industry is about 10,000 and 20,000, but we don't have that much amount of time to see how it will be. So for now, I've just done 3. Also, like as much as you increase your number of approach, your training, the accuracy will actually increase. Okay, and yeah, and yeah, there could be a case where you just need like 100 or 500 approach to train your model. So you have some sort of function saying that, okay, if the accuracy or the loss is not changing much, then stop it. Okay, so we can have those sort of mechanism to stop the approaches as well. Okay, now, yeah, and this is the summary of the model. This is how it looks like. Okay, so we had 784, then we had 128, and then we have 10. So that is the kind of model that we had. And the number of trainable parameters, this is very important. We have about 100,000 training parameters. Okay, so with this simple model itself, we have so many training parameters. You can just imagine if we start adding layers to it, what would be the number here, right? Okay, now the next thing that I want to do is I want to test the accuracy and I want to test the loss of the model that I've made. So I'm just going to evaluate it. Okay, and once I'm done with that, so I'm using my test set here because now my set is something that my model has never seen. So the accuracy that we get here is essentially the very sort of a clean accuracy, right? So like because if it can perform this nicely in a test data, uh, it's a good model. Okay, uh, just one thing, I've messed this one up. So this is entry loss and accuracy. So my accuracy is 96.53% and my loss is 0.12. Okay, so my so like the gradient descent is still not 0 yet, but it's somewhere at 0.12, which is pretty good. Okay, so once I've done that, what I'm going to do is I'm going to predict. So okay, so this would be X test. Okay, now what I'm going to do is I want to see what X test looks like, and then I'm going to see what my prediction is. Okay, so X test 0. So I'm just taking one element of it. So it looks like a 7, and my Y predict. Okay, so yeah, oh, great. So we have the Y predict as all of these, right? So these are essentially 10 because we have to predict. Okay, so these are essentially 10, right? Because these are the probability to be in each of the 10 classes. But we want to have max. That's the one. Max. So that would give us the one with the maximum prediction 7. So with our model, we got the prediction 7 as well, right? So pretty good, right? Now coming to your question, where you asked me that there are many hyperparameters, and how am I going to know which one to choose? There's something called these are all called hyperparameters. Okay, so we have yeah, so we have a lot of hyperparameters that could be. Why did I choose 128? Why did I choose only one layer? Why did I choose Relu and not Sigmoid? Right. So many decisions that could be taken here. But we need to evaluate each and every decision that we make, right? So I use something called a tensor board. What tensor board does, it gives a very nice dashboard comparing all the model that I make, okay, and it tells me which model is the best model, okay. So for that, what I'm going to do is I'm going to take my initial model. Let me know if you have any confusions here. So I'm just going to take my initial model and make it a bit cleaner, basically smaller. Okay, so what I'm going to do is I'm going to have dense layers as, like you said, why not 16, why not 200, why not 300, why not 400, why not anything, right? So 6,000, why not them? So I'll say why for I in dense layer. I'm going to make different models for my tensor board, okay? So it's going to be, um, so to define the name of the tensor board, and the way I'm going to, so there's a function called TensorFlow clearance callbacks.tensorboard, so I can just use that one. So for that, I need a dictionary of where I'm going to put all my stuff. So I'm going to put in something called logs, and then I'm going to just so that everyone is different, I'm just going to name it as the logs dash I. Okay. Uh, yeah. So and suppose that what I'm going to do is I'm going to make each and every model. Uh, And once I made the model, I need to compile it because that's one of the most important process. And once I do that, what how would I differentiate, right? So once I do that, I have to add callbacks here. Okay, and that would be my tensor board name. Uh, okay, let's hope this does not throw any errors. Okay, so once it starts running, it's obviously going to take a lot of time because it has to go through each of this layer. So I'll come back to this one later, and if I forget, do remind me. Okay. Okay. So
Yes, sure.
the now the other question is about the optimizer. So I have put the optimizer as Adam, but uh, there's one more there are a few important things that we can set in an optimizer, which is the learning rate. Okay, so the learning rate is essentially how much weightage do I want to give to the weight, each and every weight. And there are many ways in which you can set it. So one is that you can set a constant learning rate, or you can set the learning rate and the momentum is basically how fast or how accelerated your training would be. And the other one is you add all of them and decay. So decay is essentially like you're changing the learning rate as you go, which means that yeah, once you're here, you have a less learning rate. You have a more learning rate, but once you have reached in this area, you reduce it so that to not miss your global minimum. Okay, so that's also one of the major things that you might want to consider while you're creating your neural network. Okay. So once that's done, and I hope this one is clear. If not, let me know. I'll just check for any questions in the live. Uh, oh, okay. Thanks,
Yes.
Account Rajput. I have made a mistake here. Okay, cool. Thanks. Uh, yeah. So so basically, I didn't change the number of learning layer, and yeah. Okay, so thanks for that. Moving on to neural network. Okay, so how and why did this particular concept came? Okay, so what I did above is that I took each and every pixel as one. Okay, but what we want to do is that that's not how we see it, right? So once we have an image, just create an image here. It's not gonna work. Okay, fine. So it's not gonna work till the other one works. So that's fine. So once we have that image, we do not read it pixel by pixel. What we do is we read it as a group. What does that mean is, let's say if I have to remember someone's face, I might remember how the eyes look, right? Or I might remember how the geometry of the face of their faces, right? So I take out the feature of a face, or if I have to learn a letter A, I'll take out the feature of that letter A, and then that's how I'll remember it, right? So convolutional neural network is a kind of is was designed to learn the feature of the image, okay? And the convolutional neural network have really revolutionized the entire field of image processing. So what they do is, so for example, if I give you these three images, can you guess what this number could be? So Ashka, all my questions are on you, okay? Because you because I'm just communicating with you. Let's say I'm telling you that it's a number, and I'm giving you these three images. Could you tell me which number it is?
2.
It
Any
could
of
be like a zero. Yeah. Hello.
Yes, yes.
Yeah, I can
So
hear you. Yeah.
uh, looks like a 2 or a 0, I think.
Three, two,
There are comment section 387.
three. But it doesn't has like this. Oh yeah, it has this, but how will you use this? So you have to use all of them. Probably like a zero.
Yeah.
Okay, so that's what convolutional neural network do, and I think that that's pretty similar to humans read or like like save an image in their mind as well. So if we get in captcha this thing, how do we know that this is a P and not an R, or how do we know that this is a P as well, right? So we try to identify a certain feature of the letter, and we try to see what the letter would be. Okay, and that's what convolutional neural networks are. What they do is they take an area, they take the area whole together, and then they map it as a feature. Okay, so as you can see in this image, it will be like this area, this whole segment will be mapped together as one segment. Okay, uh, so that's convolutional neural network. And in this convolutional neural network, there's one more very prominent concept, which is max pool. Why do we use it is essentially to reduce the number of parameters that we need. As you've seen above, like in neural network, the number of parameter increases a lot. Okay, yeah, so what happens is in max pool layer, you take a section. Let's say said that I need a max pool with 2 into 2 filter. Okay, so you take a 2 into 2 section, you see what is the maximum value of that section, which is 6 here, and you just take the value of as 6, and you lose all the other values. Okay, similarly in this one, the maximum value is 8, and then you lose all the other ones, and so on and so forth. Okay, and the stride is true too. What does that mean is, if I have one, let's say there's a one 2 into 2 matrix which is moving, once it's in 1 1 1 1 5 6, it will move by 2. That means that from here it will just come to 2 4 and 7 8. Okay, if the stride was 1, it would have been from 1 5 1 6, it would have been with 1 2 6 and 7, right, this area. So that's your stride. So you define max pool with two things: the size of your filter and stride. And that's your max pool layer. The other way to do it is just to take an average of it. However, max pool is like more prominent, and it has been seen in many networks. So this is one of the networks where the convolutional layer is used with the max pool, and every convolution layer is used with the max pool layer. Okay, so it really helps in understanding what the feature of an image is, and in reducing the number of parameters, which is one of the very essential things. Okay, so yeah, so we have there's a network. There are many predefined networks which we will be using here as well. So there's a network called VGG, and there is like the convolutional layer, and so two convolution layer followed by one max pooling layer, and so on and so forth. Okay, so you can see that they always appear in together, and together they are like really really good. Okay, so we will try to do the same thing here. We'll try to have a convolutional neural network as well. So to do that, the one of the most important things that we need to do is essentially change the shape of the input from so we had 28 into 28, right? So we need to make it 20, a three-dimensional shape, and the way we are going to do is essentially we are going to reshape it. Okay, so this would be xstring dot shape 0. So this is essentially a 60,000. Then you have 28 comma 28 comma minus 1. So once you do that, the 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 input gets changed into three dimension. I'll just show you how. Okay, so what I can do is I can just make it 1 as well. Faster. Okay, so we had initially we had the 60,000 28 28, and now we have 60,000 28 28 1. So we didn't change anything, we just added one more dimension to it. Okay, so once we have that, we're gonna make our model where it's gonna start with sequential like we did last time, and then we're gonna have the convolutional layer. Okay, so that would be okay. So now what are the kind of parameters that we need in the convolution layer is essentially the size that we need, uh, the kernel that we need, and the activation that we need. Okay, and then Relu, because that's our favorite, and then okay, I'll talk about more of this later. The other one that I need is max pool. Okay. Okay, and this would be my max pool layer. After that, what I'm going to do is again flatten it. Okay, and then I still made a mistake. Okay, and then I will do model dot add, and then I'll again go back to my dense layers, because once that's done, I just want to get back my original layers, which was 28, 128, 128, and activation as Relu again, and okay, and then model dot add. Ten comma activation as sigmoid. Okay, any errors that you can find? Will it run? Will it not run? Okay. So this one will be. I didn't add it. Okay, cool. So yeah, so now that the model is ready, again, we're going to do the same things, which will be the compile and the train and fit one. Okay, it's got interrupted. I'll run this again. Uh, so, yeah. Okay, so this got interrupted. Uh, okay, let's try running it again. I'm not sure why and how. Okay, so yeah, that's all. So, Ashka, you were saying something?
No.
Cool. So once that's done, we'll run this one as well. Okay, I'll just check what's going on there.
Did we get results for the hyperparameters?
Yeah, I think that got interrupted somehow. I'm not sure how, so I just had to run it again.
Okay. Also, one more thing, like, are there different types of layers that we can add? Like, you're adding dense type of layers. Are there some different kinds of layers?
Yeah,
That,
definitely. Like there are many types of layer that you can add. We'll just see those. But the ones that I'm talking about are uh, essentially used in every network. Uh, yeah, so there could be, okay, so these are activation, these are initializer. I'll talk about this in a while. Uh, yeah. And core layer, yeah, so you have the core layers as your input layer, your dense layer, your activation layer, embedding layer, masking layer, and lambda layers. So I'm not going to talk about these
okay.
as much.
Yes, yes,
Okay.
yes.
So these are essentially used when you have to, I think when you have to uh, take like one. So have you seen those green images of like there's a car and then the rest of it is green, or the way they make the movies like the Avengers and stuff like that, so they have all the green screen, or the way they make Game of Thrones, right? So they have everything green. So the masking layer, I think that that's what they help to do. Like they'll just have one part of it and the others would be green. uh, yeah, now let's just see if this work is working. Okay, so by the time this works, I'll just show you what you have to do. Once you get this, let me know if my terminal is visible to you. Can you see my terminal?
Yes, yes, it is.
Okay, so once you have that up and running, what you do is
Can you
you go to your,
maximize the terminal?
yeah, yeah, sure. Okay, so you go to your desktop, so you go to your working dictionary, wherever you have that logs file. I'll just show you where mine is. So mine is essentially so I have a in desktop, I have a file called Women in Data Science, and in that I have all these logs. So the random numbers that I've put in here are all here. Okay, so 16, 200, 300, 400, 60,000, everything like whatever I put, it'll just come here. So you, from your terminal, access that file. Yeah, so access that file, and then you can have like this is the command that you'll have to run, which is tensorboard log dir logs. Once you run that,
Right,
you'll sorry.
right, right.
Okay. Yeah, so once you run that, you will yeah. So it will just try to. It'll give you a link, a web link, and you just need to copy that link and put it in your browser and use that link.
Okay.
Okay, so it has given me my link here. Okay, so I'm just going to use that in my browser. Uh, okay, so what it'll do is it'll give me all the results that I have, and it'll tell me what my accuracy per epoch was. Okay, so it'll tell me that 16 was about uh, and I can also like just look at one of the results. So let's just look at 16. How does that look? Okay, so it increased uh, from a value of 0.90 to a value of 0.92, and the highest value could be seen as about 0.92 as well, right? So that
Right.
was my 16, and the loss is about, let's say, yeah, you can actually read the smoothened value, which is 0.31, 0.13, sorry, 0.34. Okay,
Three one.
so yeah, and then yeah, and then you can compare two of them together. Okay, so you know what the value of your 16, if you have 16, what your value is, and if you have 200, what your value is. Okay, uh, and similarly, you can see your accuracy or loss, whatever matrix you think is more important for your data. I think that's what you should be looking at. Okay.
Okay.
Yeah. So does so why I use this is because so the other way that you can do is you can actually make graph in your Python itself. But I think that this is a lot more convenient and it gives you a full view of every data, and it's easier as well. Okay.
Right.
So yeah. So yeah, that's something which is interesting and nice. So I'm just going to stop this now because I think we have to do more stuff, and we're almost about time. Okay. Yeah. So once you have that, I'm not sure. Uh, and also, I forgot to change my train here because I made a train CNN, and I don't need the tensor board name at the moment, so I'm just gonna remove it. Okay, and yeah, let's just see if this works. Yeah. Okay, so the other thing in this, what we want to see is that which one is more efficient. With three layers, generally you can't tell because everything changes as soon as you change layer. Ideally, convolutional 2D is many times more efficient than dense because you try to capture the features, okay, and which is why it's like much more efficient and widely used, okay, especially whenever image is concerned. Okay, so moving on, I just want to talk about this very interesting feature called transfer learning. What it is that there are many people who have participated in a competition called ImageNet. Okay, so what they have done is they have over the time made a lot of networks which are huge. Okay, so we were just at 100,000. These guys have made networks 100 times of that size. Okay, so these are the number of parameters that they have. These are the models that they have built. This is the size of the model. This is the accuracy that this model gives. So they're pretty good, like 90% accuracy, 94% accuracy on random data. They're pretty good. So what we want to do in transfer learning is that we want to harness this capability, okay, of uh, of these models, and but we don't want to train so much, right? Because not everyone has this kind of
Computational power.
infrastructure, yeah, and computation power as well, right? So what we're going to do is we are going to use Inception V3, and we're going to see how we can use that in MNIST, our data set. Okay. Uh, yeah. So okay. So before that, just a quick note. I'm getting an accuracy of 84,897 here. Although you shouldn't compare test and train accuracies, but I think this might do better than the previous one without convolutional neural network. Okay.
Right.
Yeah. Yeah. Okay. So moving on to our Inception model. Uh, yeah. So basically, Keras is like, okay. So Keras is like very nice language if you want to start neural network with. It has every function on your fingertips. So it also has the Inception V3. And what we do is we take this network. Okay, we put certain layers before and after this layer so that our input is as we wanted, what as output is, and our output is how we want it. And apart from that, the weights will use from this layer itself, so we don't have to train our weights again and again. Okay, so that sounds like pretty interesting idea, and everyone can do the analysis quickly and fast and yeah, whatnot. Yeah. So what I'm going to do is uh, Yeah, so I got the Inception V3. I have some pre-processing which I might not use. Okay, but in any case, the first thing that I have to do is I have to make my base model. Okay, so my base model will be Inception V3. Uh, the the weights that I want in this is ImageNet. Okay, and then input shape that I want is 75, 75, 3. So why this extremely random number? So what happened was I ran it without this input number, input shape, and my initial input shape was 28 into 28, right? Into 1, 28 into 28, 1, right? It threw me an error saying that this particular model needs that much input shape. Okay, so what we have to do is before using this model, we just have to like change our input in such a way that it's at the very least 74, 74, 3. Okay, so that's what we'll do later. Once we have that base model, okay, and
Just
then
to
we
note,
have to,
Kirti,
yeah.
it's okay. Take your time.
Oh, okay, okay. Yeah, cool. Thanks. Uh,
So there are a few questions. We'll take the questions at the end of the session.
okay, okay. I was just looking at that. Yeah, okay. So an include top is equal to false. Okay. That also, if we do include top equals to 2, that will increase our input shape, and we don't want that because, see, our image is not great, right? So we want it as minimum change as possible. Okay. So once we have that, what we'll do is uh, we'll say that our layers should not be trainable. Okay. Because if we begin to train that many layers, we'll have this session till next year probably. Okay. So yeah. So for layers in base model, dot layers, okay, and then okay. So that's how we just said that we don't want to train that layer. We don't want to change it. We'll use it as it is. Okay. Uh, yeah. And then we build the model. Okay, I have this already, but I'm just going to delete it and then I'm going to write it again. Okay. So what we do is we define so now we have to define the model a little bit differently. So what we'll do is we'll say base model dot output. Okay. Output or outputs. Output. Okay, cool. Yeah. So this one. The next, what we're going to do is we are going to take this output. We're going to put it into a dense layer again. So we're going to say dense, and again 28 comma activation is our favorite, and then we have to write X here, okay? Because this particular model, this is not the usual model that we have defined till now. This is just the input and the output that we are defining. What that means, I'll just tell you. Prediction is equals to, and now the final uh, prediction layer, which will have 10 comma activation as our second favorite, sigmoid. Okay, and then again we'll have X. So this is not how we have defined the model yet. This is just the inputs. Okay, define. Okay. uh, okay, so the next one is now we have to define the model. Now this model will have something called keras.model. Models is already there. Okay, so model. Okay, so there's a library called keras.models model. So we're just going to use that. We're not using sequential this time because we are just going to define our input and our output. Okay, that's all we're going to define this time. So what we're going to say is our inputs will be the base model dot uh, dot input. Okay, so we need our base model input, and our output is going to be our prediction. Okay, so that's all we have done. And once we have done that, again, we'll just use model.compile, and we have optimizer, add them again, and then loss. And again, like TensorBoard, you can experiment with these as well. Which one goes well with your model? But again, thing is that you can't
Maybe,
experiment a lot, right?
can you just zoom in a little? We have got a request to zoom in.
Okay, okay, let's just do that. Is that better now?
Yes.
Okay. Uh, okay. So my loss was
Sorry to disturb you in between.
no worries, no worries, all good. And my matrix is yes, you can experiment with all of them, but like I was saying, it's not always possible to experiment. So your experiment should be designed in a way that you know what the results are, like you understand the characteristic of your data. What change are you making while you're experimenting with various sort of models, okay, and why are you changing that? So that's very interesting and very difficult to do. Okay, so once that's done, we will do. Okay, yeah. So now we have made the model. Okay, I'll just try to run it, see if I'm getting any errors. Once I've done that, I remember I have to change my input because this is the size of input that I need. And I have just 28 into 1. Should not take that much time. Okay, we'll see. Oh, it didn't. Okay, good. So to change the data, what we need to do is first we need to change the data to 3 channels, right? So we had 28 into 28 into 1. We need to make it 28 into 28 into 3. Then we are going to change that 28 into 75. Okay, so there are 2 steps process. Uh, so so this we are doing for transfer learning, and what we're going to do is um, uh, so we are essentially going to do so X train that we had, will reshape it to something comma 784 784 748 uh, comma 28 into 28. Okay, okay, and once we have that, we're going to multiply it by 3. What does that do is it's going to make my layers like this, the layers that I have already, it will just multiply it by 3, and then I'm going to reshape it as something comma 28 comma 28 comma 3. Okay, so why I have done -1. So why do we generally use -1 is that we say to the program that use anything that you would like. Okay, whatever is remaining from what we have used already, just use you like just have that dimension here. Okay, that it'll be 60,000, but we just don't want to write 60,000. It's just yeah, that's what we do. Okay, now we have to resize the model to the 2744. So for that, what we are going to do is we will convert this array into image, and then convert that, and then read it at 75. Okay, so what we'll do is we have this image to array. Uh, Again, a beautiful package in Keras. Uh, if you have Keras, you don't have to worry about anything. Why we can't use Keras always, I'll talk about that as well. So we have image to array. We have our image as, let's say it's IM. Uh, okay, and we are just going to do scale equal to false. Okay, now once we have that, we'll do array to image. So it's so much drama we're doing. And once we do that, we're going to, so once we are reading it again, array, we are going to resize it to 75 comma 75. Okay, uh, yeah, and then what we're going to say is np dot as array and we don't know what IM is right now, right? So we're just going to say uh, for IM in string dual. Okay, so that would be our new string dual. I'm just going to call it 2 so that I don't get confused. Uh, okay, so this one goes there, this one goes there. Okay. Okay, so what I'm going to do is I'm going to see my cheat sheet and we'll count it as 2 Googles. And I'm just going to use this one here. Okay. Okay, but you understand the concept, right? If not, let me know. I'll just explain it again and try to code it again. Uh, yeah. Okay. So once we have that data, we have the labels as well as the one hot encode labels that we made. We're just going to print the extreme TL dot shape. Okay. Okay. And once that one is ready, we put our data there. Yeah, that's ready. This is going to take some time, but now it's ready. We are going to take this and then white string. Okay, and then we got an error again, and we didn't define. Which, uh, okay. That calls for another cheat sheet. Gonna get this today.
Yes.
Sorry about that, guys. It's just I don't
No,
remember
no.
what's wrong
We're
here.
coding along, so
Yeah. Okay, it's saying that.
we all need a cheat sheet sometimes.
Yeah.
And like up till now, the Google count is pretty low. So
Yeah. Yeah. Let's see. Okay, so okay, let's copy it. Let's just increase the Google count to 100. Okay, so yeah, so again we had the same thing. This is essentially white chain. I have to zoom in, like zoom down a bit, because okay, so by the time it's running and loading, I'll let's talk about yeah, okay, so this was something interesting that I just wanted to show. So I have been talking a lot about feature maps, okay, and what are they and why are they used and how are they used. So what I've done is I've taken another model called VGG16 and I've taken a random image. uh, the image I'll just show you here. It's actually it's image of a dog, okay. What I wanted to see is yeah, so I hope that's visible.
yes,
So what I wanted to yeah, okay, so what I wanted to see was that what are the kinds of feature maps the a model makes, okay. So what I did is I use that model as VGG, and input as the image of the dog and the output as the 16th layer, just some random layer. and what are the kind of features that we get. Okay, so this is what came in that. Like some of them are pretty. Some of them, yeah. So like as you go down, you can see you can. Okay, so this one was so 16th layer didn't give a lot of good features. I'll just run this for one layer. You can see almost every feature has some kind of dog in it. So either his paws will be highlighted, or the eyes will be highlighted, or something like that. We'll just run that now. Probably 16th layer does not has that kind of features, or it's not quite visible. Uh, yeah, so but like you can see the kind of features that each and every layer has in the network. Okay, I'm sure there are many websites which show you the features also, features of image network. Like it'll give you a good understanding of what kind of features are we looking at. And maybe I'll just go to the images. Yeah, okay. So this one is good. So if you can see, like for a person, you can actually see the eyes, right, the hair, and stuff like that. So every layer can actually help you see what kind of feature it is capturing. Okay, so you can like research a little and run the models a little bit longer, because honestly, like 3 to 4 approaches won't do any good to your model. So when you do that, you can actually see what kind of features a model is extracting. So that was pretty interesting for me. Uh, and the transfer learning has started to train, which is good. Uh, and so I'll just go through the code once again. What I do is I take the base model. I say that the layer should be false, and the base model as. So I take yeah, and then the input for this would be the input for my model is this one, where I say that take the output from the base model, do some sort of learning on that, and then predict my required number of layers. Okay, and then model it, optimize it, and change the size uh, of the uh, okay, change the size of the image and just fit it. So that's how I'm going to get my model evaluation. Okay, the plus point is that I get to use the power of this particular huge Inception v3, and I don't really have to train it, right? So like actually 7:33 is pretty good timing for such a large model to train, right? So yeah, so I have personally used this a lot, and it's I think everyone knows that this is the most efficient way to train a neural network. Yeah, so we have covered the future maps as well. Uh, so I'll show you these in a while. Okay, and now like Keras seems to be very good and nice and easy to start, but it's not an idle language to use. It's hard to debug, and it's very slow. Okay, PyTorch, on the other hand, is like very fast, and it's easy to use. It's quicker to debug, and it's actually more faster than TensorFlow many a times. And Yeah, again, the problems with TensorFlow, it's very hard to code. Okay, so the current code that you see in Keras, which may be like 10 lines, could go up to like 50 lines in TensorFlow easily. But again, it's very flexible and portable, so you can actually use it with a lot of different languages, like uh, a lot of different software packages. That's why people generally use it. I personally prefer PyTorch a lot. And just to showcase you how PyTorch coding looks like, so it would be like, so it's the same as the above one. So for MNIC data, I'll load the data. I'll use one of the batch size. I'll make my model, then define the logs, the input, the optimizer, and so on and so forth. And then instead of just saying that fit it and run these number of reports, I actually have to run each report and see what the optimizer value and the output and the loss is. Okay, so this gives a lot of flexibility. Actually, it looks bigger, but it actually gives a lot of flexibility. So yeah, so that's a good language as well. If you want to try out, you can try out PyTorch. Great documentation. You can easily use it. TensorFlow, I didn't really showcase here, but I've mentioned that this is the TensorFlow documentation, so you can probably look into that. And then again, there are many ways in which your neural network can be improved. One obvious way is that you can have more data, and you can have more hidden layers. So it has been seen that more number of layers, you'll have better optimization. Better results. But the gradient descent will be a problem which you'll have to deal with. It has also been seen that initializing the weights instead of just saying that they're zero. So if you don't initialize, you just say that they're zero. If you do that, then that will also improve the way the neural network learn. And then the learning rate that we talked about a bit above, that will also help you to improve your neural networks. And of course, transfer learning. It's really helpful. I'm just using a Mac Pro right now, and I can use that power. So I think it's really nice. Uh, yeah, so that's about it. We'll see how when this stops. Till then, I'll just answer the
Yeah,
questions.
I'll just read out the questions.
Yeah.
You you can continue with that at this screen.
Oh, okay.
So, so Jaren Joseph is asking, when running CNNs on more complex data, do we have to
Mhm.
run it on bigger machines, like with more computational power?
More computational power is always welcomed, especially for training neural network. However, of course, like you wouldn't want to waste money on getting that power all the time. So what you can do is you can use the Google Colab. Okay, what the the first thing is that it's free. The other thing is that it's so I'll just open a notebook. It'll give you a GPU instance. It can also give you a TPU instances at time if you're lucky. And So you just go edit notebook, okay, and notebook settings, and you choose a GPU. Okay, so this will give you an easy access to the GPU free of cost, and it's very reliable. I've done many projects in this. The other thing, if you're a student, you can get Google Cloud. I think $500 free you can get Google Cloud computing. Okay, so that you can get, and AWS also I think gives you about $25 to $50 free. I'm not sure about the cost, but yeah, if you're a student, both of them gives you free of cost GPUs. But if you're just starting out, then try to just train your model in your local computer, and if you're facing problem, then use this options. And of course, like Google Colab is very easy. It'll just give you the same view as you have in your Jupyter notebook. So yeah, that's really easy.
Okay. The next question we have is, when to use Kera's sequential API and when to use the functional API.
Sorry. Oh,
When should we use the Kera's sequential API and when to use the functional API?
uh, functional API was the model one, is it? The transfer learning one. Is that what you're talking about?
Yes.
I think, right? So essentially, like Keras sequential, when you're making a model and you know that one sequence is after the another, then you use the Keras sequential one. Model one you generally use when you have your input, when you want to define just your inputs and outputs, like we did in. So if you see the model that we defined uh, 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 in this one, it's essentially like we are just defining the input and the output, right? Uh, and everything else is just defined on our input and our output and nothing else. So that's when you just use the model. Otherwise, you'll use the sequential when you're actually defining that this layer after this layer and after this layer. So yeah.
Okay. So one question was like about the log stuff that you showed for the tensor board. So I think in
Yeah.
the Google Colab you have mentioned resources for learning about the tensor board or TensorFlow.
Tensor board, probably not. But yeah, I can add that later.
Yes, please if you could add
Like
this.
we're posting this notebook, right? So I can just add that one as well.
Yes.
Uh, we would ace our exams. Yeah, that's a dream, Jaren. Okay. Yep. Okay. Uh, is that all the questions?
Yes, that's good. If
Yeah.
anyone has any questions, you can post it in the comment section. Is the model done training? I don't think.
No. Did it just run an error? Oh no, this one is. Yeah, no, it's still training. So yeah, one is done. The loss is coming out to be very high. But yeah, it generally decreases with time. So yeah, we need to give it some time.
So usually, when you are practicing, how many epochs do you use? Like,
Uh, yeah, so when I'm not using any GPU, I generally stop it at when I'm using Google Colab, I generally stop it at 2000. There are instances when I just did 20 and I submitted my projects and my reports. It really depends on the amount of data that I have and the amount of time taking to train. But yeah, like ideally, I would like to do 2000 times, but that never happens. So yeah, I mean that rarely happens. Let me just say that.
so I guess we can post the Google Colab in the section down below for
Okay.
everyone to see
Yeah.
later on when it's done training, so you can see the results.
Yeah.
It was really great. The session was really great. We got to learn a lot about TensorFlow and
Yeah.
neural networks and the feature maps, interesting stuff. So thanks a lot, Kirti, for joining us today.
Thanks for inviting me.
It was really fun. And since you were coding
Yeah.
along, so we could actually see like how the library is being used and stuff.
Yep. Yep. Yep.
Thanks.
Thanks a lot, Ashka. Okay, guys.
Awesome.
Nice to see you. Okay. Sorry. Uh, yeah. Nice name, but I've never heard this name before. It's a really
Yes,
nice
I
name.
get that a lot.
Okay. Okay. Bye bye. See you guys. Let me know
Thank
if you have any questions. Yeah. Bye.
Yes, thank you. Bye.